Since most acid-base reactions take place in the presence of water, it is important for us to understand how acids and bases interact or react with water. So we're going to start out with dissociation, and we know that bases are always the substance that dissociate, and a dissociation reaction is a simple reaction in which a substance, in this case the substance is a base, solid sodium hydroxide, when placed in water, dissociates by breaking up into its constituent ions, meaning the two ions that it is made up of, and obviously because these are now in water, they form an aqueous solution of positive sodium ions and negative hydroxide ions. So when we say that a substance dissociates, all that we are saying is it breaks up into its constituent ions and forms an aqueous solution with water. When we draw or write water on top of the arrow, as I've done here, we're doing that to show that the sodium hydroxide is not reacting with the water, but only dissolving in the water. By contrast to that, we know that acids undergo ionization when placed in water. Now, ionization is essentially a two-step process. The first step is when we decide to add an acid to water. In this case, we are adding gaseous hydrochloric acid. The first step in this process is exactly dissociation, in which that acid breaks up into hydrogen ions and chlorine ions, both in aqueous solution. That is the first step in the ionization process. The second step in the ionization process is where the positive hydrogen ions react with the water. And we know that water is in the liquid form here, so the positive hydrogen ions react with the water here to form an aqueous solution of hydronium ions, H3O+. So these two steps can be written as one combined, where we just say that the ionization process is where we start out with an acid that is added to water, and that reacts to form our hydronium ions and chlorine ions, both of which are aqueous because they are dissolved in water. So to summarize, we know that bases dissociate in water, which is to say that they do not react with the water, they break up into an aqueous solution of their ions. And acids ionize in water, which is a two-step process. The first step, which is dissociation. The second step is where the hydrogen ions actually react with the water molecules to form hydronium, and that can be written as a single step known as ionization. It is important for us to understand the concept of strong acids and bases because their strength will determine the properties of the products that are formed in their reactions. So we know that a base, for example sodium hydroxide, when it is solid it is placed in water, and we know as it's placed in water, because it is a base, bases dissociate in water to form a solution, an aqueous solution of sodium ions and hydroxide ions, both dissolved in water. Now, by definition, a strong base is one that dissociates completely, basically saying that if we start with a 1.2 molar solution, meaning moles per cubic decimeter, solution of sodium hydroxide, all of that will dissociate, which would mean that we would end up with a 1.2 mole per cubic decimeter solution of hydroxide. So we say a strong base is one that dissociates completely in water. In the same way, strong acids also dissociate completely. So we would say when we place gaseous hydrochloric acid in water, we know that acids ionize in water, and that basically means that they first dissociate and then react with the water to form an aqueous solution of hydronium ions and chlorine ions, also aqueous. So when we say that it is a strong acid, What we are saying is that all of the acid dissociates and then ionizes to become hydronium. So once again, the entire concentration of the acid that you start with becomes the concentration of hydronium. These are the common strong bases: sodium hydroxide, potassium hydroxide, and lithium hydroxide. The common strong acids are hydrochloric acid, nitric acid, and sulfuric. Most other acids and bases are considered either weak or medium, and it is typically these that are considered the strong acids and bases. It is important to realize here that the strength of an acid is completely independent of the concentration of that acid or base. So it is possible to have a very low concentration of a strong acid or a strong base. All that would mean is that it is still completely ionized or dissociated in water, whereas when we say that we have a high concentration, we are just saying there is a large number of moles per cubic decimeter of that substance present. There are largely two theories that we use to explain the behavior and properties of acids and bases. The first of these is the Arrhenius theory, that is used specifically for acids and bases in aqueous solutions. So the Arrhenius theory defines an acid as any substance that produces hydrogen or hydronium ions in water. We know that this happens through the process called ionization, where we start here with nitric acid. It reacts with water in a two-step process that we know the first step is dissociation and the second step is then the reaction with water, but ultimately the result is that we form aqueous hydronium ions and nitrate ions in solution. So as we can see, an Arrhenius acid has produced hydronium ions, therefore HNO3 is an Arrhenius acid. By the similar definition, we say that an Arrhenius base is a substance that produces hydroxide ions in water. So if we take one of our common strong bases and we place that in water, we know that when potassium hydroxide is placed in water, it will dissociate. And dissociation, we know, is a simple reaction, or not a reaction, but where a compound breaks into its constituent ions to produce potassium ions and hydroxide ions, both in aqueous solution. So the Arrhenius theory is specifically aimed at explaining the properties and behavior of aqueous solutions of acids and bases. An Arrhenius acid is any substance that produces hydrogen or hydronium ions in water, and an Arrhenius base is any substance that produces hydroxide ions in water. The Bronsted-Lowry theory of acids and bases relates specifically to the transfer of protons. So the main advantage that this theory has over the Arrhenius theory is that this does not necessarily have to be in the presence of water where these reactions would happen. So by the Bronsted-Lowry theory, it says that an acid is a proton donor. When we speak about a proton here, we are speaking about a hydrogen ion. And so we can see that an acid is a proton donor in the following reaction, where we start out with hydrochloric acid and we react that with water. We know in the Arrhenius theory of called this process ionization. And what we show here is we show that the hydrochloric acid donates its proton to the water molecule, thus leaving a chlorine ion, as well as creating a hydronium ion. So you can see here that the result of the Bronsted-Lowry theory is the same as in the Arrhenius theory, but the explanation for how that has happened is slightly different. In the same way, we can say that a base is a proton acceptor, and what we can do here is we can show that this is possible with ammonia when it reacts with water, because we can see that the ammonia is able to accept a proton from the water molecule which means that the ammonia becomes NH4 with a positive charge, and that is aqueous, and it leaves hydronium or hydroxide ions behind. So once again, the result of this reaction is the same in that it produces hydroxide ions. So by Arrhenius theory, it is also a base, but the explanation for why that has happened is different. Where we have said in Bronsted-Lowry theory, we're talking about the transfer of protons, where an acid is anything that can donate a proton, and a base is anything that is willing to or able to accept a proton. You will see here that water is able, in this case, since the hydrochloric acid is our acid donating the proton, that makes the water the base. And in this case over here, since the water is donating the proton, that makes the water the acid and the ammonia the base. And we call that property an amphiolite. We say that water is an amphiolite because it is able to act as both an acid and a base. The Bronsted-Lowry definition of an acid as a proton donor and a base as a proton acceptor leads to there being conjugate acid-base pairs, which is a pair of compounds that differs by a single proton or a single hydrogen ion. This can be seen in any acid-base reaction. So over here we have hydrochloric acid, which we know is our acid, and ammonia, which we know is our base, which means that by the Bronsted-Lowry theory, the acid will donate a proton to the base. That then creates a negatively charged chlorine ion and a positively charged ammonia ion. What this then tells us is that since NH3 has now accepted a proton, an additional proton, one more than it originally had, to become NH4+, we can see that NH4+ ammonium is now in a position to donate that proton that it has just received. So we say that it is in a position to be an acid, but it is only in that position because it has already received a proton. So what we say is it's not a normal acid, we say that it is a conjugate acid of this base. So this is our first conjugate acid-base pair, which shows that the base is NH3, ammonia, but once it has received a proton, it is in a position to donate that proton, which makes it an acid, but specifically the conjugate acid for this base. In the same way, this chlorine has given its proton away in the initial reaction, which means that it is now in a position to receive or accept a proton, which means that this chlorine is now essentially a base. Once again, it is only a base because it started out as an acid, so we say that it is the conjugate base for this acid. So if we see this reaction as a reversible reaction, we can now see that the reverse reaction would be where our conjugate acid donates its proton to the conjugate base to get back to our original reactants. We can see this again in a second, or a separate reaction. Sulfuric acid we know is an acid, and it would therefore donate its proton to the water molecule. That makes water, in this case, the base. And what we can see here is that since this sulfuric acid has donated a proton, it is now in a position to receive a proton. We can see that it has a negative charge, which makes it a base, but specifically the conjugate base for the original acid. In the same way, we can see that hydronium is related to water by a single proton. It is now in a position to act as an acid, but only because it was originally a base. So we say that it is the conjugate acid of this base. So the reverse reaction here would be, or would see the donation of the proton from the hydronium back to hydrogen sulfate. In all of these reactions, you can see that the conjugate acid-base pair are related by a single proton. This one is NH3, this is NH4, this is HCl, this is Cl. So they have both either gained or lost a proton. And over here we have H2SO4 becoming HSO4 with the loss of a proton, and H2O becoming 3O, the gain of a proton. Finally, we can also see that if something is a strong acid, as we have in the case of hydrochloric acid, the conjugate base is typically going to be weak, whereas in this case we have a weak base to start with, which would mean that our conjugate acid is then a strong conjugate acid. So conjugate acid base pairs are often inverses of each other. If you have a strong acid, you would have a weak conjugate base, and if you have a strong base, you would have a weak conjugate acid. Since water is an amphiprotic substance, meaning it can act as either an acid or a base, we can say that water undergoes auto-ionization, which basically means that it ionizes itself, where one water molecule would act as the acid, another would act as the base that receives that proton, and we see that that would then form hydronium ions that are obviously in aqueous solution and hydroxide ions that are also in aqueous solution. Fortunately, this is a reversible reaction, and since it is a reversible reaction, that means that this reaction has an equilibrium, and we can calculate the equilibrium constant for this reaction, which is found by the product of the concentration of the two products there, hydronium and hydroxide. And experimentally, this value is found to be 1 times 10 to the power of negative 14, and this is at 25 degrees Celsius. What this tells us is that the concentration of hydronium ions in this solution is then 1 times 10 to the minus 7 moles per cubic decimeter. This auto-ionization of water allows us to define a neutral or a midpoint on our pH scale. We know that the pH of a substance can be calculated using the log base 10 of the hydronium concentration. And so what we can see here is that negative log base 10 of 10 to the power of minus 7 can be simplified as negative 7 log base 10 of 10. So what this tells us is that the pH of water is 7, which we can define as our neutral point on our pH scale. Since this equilibrium constant is a constant at a specific temperature, we use this as an identity known as the ionic product of water, because this identity, the concentration of hydronium multiplied by the concentration of hydroxide, is equal to 1 times 10 to the minus 14, means that we have an inverse proportion here, which allows us to determine when the hydronium concentration increases, the hydroxide concentration would decrease, and vice versa. We know that the pH scale is our way of indicating how acidic or basic a substance is, and essentially what that does is it does that by measuring the concentration of hydronium ions present in a solution. And the reason why hydronium ions works even for acids and bases is because we know from our ionic product of water that the hydronium ions are inversely proportional to the concentration of hydroxide ions in that solution. So our most simple example is we are given a strong acid. We are told hydrochloric acid is added to water, and that has a solution or a concentration of 9.77 times 10 to the minus 4 moles per cubic decimeter. Now, since we know that strong acids are acids that dissociate completely in water, and hydrochloric acid is a strong acid, that means that since the ratio of hydrochloric acid to hydronium is 1 to 1, that means that there must be 9.77 times 10 to the minus 4 moles per cubic decimeter of hydronium present in the solution, which means that we can use our pH calculation over here, the negative log of that hydronium concentration, 9.77 times 10 to the minus 4 moles per cubic decimeter, to find that the pH for this hydrochloric acid solution is 3.01, which we can see is a pH of a fairly strong acid. The bases are slightly more complicated in that we have a certain amount of sodium hydroxide, which we know is also a strong base, which means that it will dissociate completely in water. So we've been given the concentration of sodium hydroxide. Again, the ratio of sodium hydroxide to hydroxide is 1:1, and it dissociates completely, so we can then safely say that the concentration of hydroxide must then be 9.52 times 10 to the minus 4 moles per cubic decimeter. But that is our hydroxide concentration and not the hydronium concentration. So there we use the ionic product of water, which is this identity that says the concentration of hydronium multiplied by that of hydroxide will always be 1 times 10 to the minus 14 in water at 25 degrees Celsius. So we can then substitute our hydroxide ion concentration in here. And solve to find the hydronium ion concentration in the solution, which we find to be 1.05 times 10 to the minus 11 moles per cubic decimeter, which we then know we can substitute into our pH calculation, the negative log of that hydronium concentration, to find that this solution of sodium hydroxide has a pH of 10.98, which makes sense once again that this is a fairly strong base. So this is an easy calculation when you have strong acids or bases, because you know it dissociates completely. When it is a weak acid or base, we would have to be given the Kc value so that you can calculate where equilibrium lies and what percentage or what proportion becomes products, and then you can calculate the concentration of your unknown from there before proceeding. You will see that it is also at times possible to calculate the pH by using something called pOH. So it's just 14 minus essentially the inverse of our hydronium concentration. We prefer not to teach this method, as the way in which it is marked in exams is sometimes unclear. So we rather use this method that is always marked correctly and in the same format. We know that the neutralization reaction between an acid and a base will always form salt and water as the products. And we are going to look at those salts through a process called hydrolysis, which is essentially how those salts react with the water that is formed. And there are 3 scenarios that we're going to look at. The first one is the reaction of a strong acid, hydrochloric acid, with a strong base, sodium hydroxide, to form salt, and a sodium ion that comes from our strong base and a chlorine ion that comes from the strong acid. We can therefore say that the sodium ion must be the conjugate acid for this base, and because sodium hydroxide is a strong base, we know that the conjugate acid would be weak. In the same way, we know that the chlorine ion comes from the hydrogen chloride acid, which makes them a conjugate acid-base pair, which means that this is the conjugate base for the hydrochloric acid, and once again, it was a strong acid, and therefore this is a weak conjugate base. For the hydrolysis reaction, we would look at these and we would say, how does a chlorine ion react with a water molecule? And what we can see here is that because it is a weak base, we know that it is very unlikely to be able to take a hydrogen ion away from a water molecule. So we can therefore say that there is no hydrolysis between chlorine and water, or no hydrolysis reaction. In the same way, for sodium, we can see that sodium, being a weak acid, does not have a proton to donate to the water, and therefore cannot donate or hydrolyze with the water. So since there is no hydrolysis reaction with the water, there is no further product formed. We'll see what exactly we would expect to form in the next 2 examples, but that is why we can safely say that this is a neutral salt, because we can see that a strong acid would completely neutralize a strong base, and the salt would then be a neutral salt. This is in contrast to a reaction where we have hydrochloric acid again, which is our strong acid, and ammonium hydroxide, which we know is a weak base. Once again, it forms water, and then the two salts that it forms, the ammonium we can see very clearly is the conjugate acid for this ammonium hydroxide base, and since it is a weak base, that must mean that it is a strong conjugate acid, and once again, the chlorine is our weak conjugate base for the hydrochloric acid. So the only new substance here is the ammonium ion, and we are going to see that that ammonium ion undergoes hydrolysis with water because it is a strong conjugate acid, meaning it is capable of donating a proton, and since it can donate a proton to water, it will form more hydronium ions and obviously some ammonia. But this hydrolysis, the hydrolysis of ammonium with water, clearly shows that our products actually form some ammonium, and what that implies is that even though we have a neutralization reaction between an acid and a base, our salt, the ammonium chloride molecule, is still acidic because we had a strong acid and a weak base. So the implication here is fairly standard in that we would expect that a strong acid plus a weak base would form an acidic solution, but now we can see that that solution is acidic because the salt that is formed is able to hydrolyze with water to form more ammonium ions. And then finally, if we have a weak acid, this is ethanoic acid, and react that with a strong base, sodium hydroxide, once again we form water. The conjugate base for this weak acid would obviously be a strong conjugate base, and the conjugate acid for sodium hydroxide would obviously then once again be a weak conjugate acid. So the only new substance here is this substance over here, and we are going to see that that is able to hydrolyze or undergo hydrolysis with water, once again because it is a strong conjugate base. We know that it is a base, meaning it will accept a proton. The fact that it can accept a proton means that the water molecule loses a proton, and we form that same ethanoic acid once again, but more importantly, we form hydroxide ions. And those hydroxide ions we know affect the pH of the solution and make the solution more basic. So once again, the implication makes sense in that a weak acid plus a strong base is going to form a basic solution because the salt that is formed is basic. A titration is a lab technique in which the concentration of an unknown substance can be determined by reacting it with a certain amount of a known substance, known as the standard solution. The setup is usually as follows, where we have the standard solution. Standard solution means it is a substance in which the concentration and volume are known for that substance. So the standard solution is something that we would prepare. In this example, we have prepared a 0.1 molar solution of hydrochloric acid, and that is placed in the burette, which has this valve here which allows us to control the amount of substance that is added into our unknown substance, which we know is sodium hydroxide. We do not know the concentration of that solution. What is important for the unknown is that we know the exact volume of that solution that is added, and for that we use a pipette. The pipette normally comes with a fixed volume that it can measure, and you would use that to deposit the exact volume of substance into the conical flask. Once you have the titration set up in such a way where you know the volume of unknown substance and you know the concentration of the known substance, you would then start the titration where you have an indicator. Your indicator, in this case, since we have a strong acid and a strong base, that means that we will form a neutral salt. Since we know that the salt is neutral, we are looking for an indicator that would indicate in the range of neutrality around a pH of 7, and that would be bromothymol blue, which is yellow in an acid and blue in a base. So we would add the indicator to our unknown substance, so it would start out blue in color. We would then slowly or systematically add our standard solution of known concentration to our unknown, and we would continue this until we reach the point known as the equivalence point. The equivalence point is the point at which equal amounts of acid and base have been added to the solution. So in this case, it's the point at which the number of moles of hydrochloric acid is equal to the number of moles of sodium hydroxide, and we know that because the indicator will indicate exactly halfway between yellow in an acid and blue in a base. Once we know that, what that then tells us is we know exactly what volume and concentration of standard solution has been added. We also know exactly what volume of the unknown solution was present at the start, so we can say the following. Since we know that our ratio of hydrochloric acid to sodium hydroxide is 1:1, what that tells us is that the number of moles of HCl at this point, at this equivalence point, must be equal to the number of moles of sodium hydroxide at this point. The number of moles of HCl can be determined by multiplying the concentration of our standard solution, 0.1, by the volume that we have determined from the burette. In this example, we found that to be 17.3 cubic decimeters, and we know that that must be equal to the concentration of that unknown substance multiplied by the volume, and we know that we started by adding 25 cubic decimeters of this solution, which means that we can then solve for the concentration of this unknown substance to find that it is 0.0692 moles per cubic decimeter. So this titration technique has allowed us to use a standard solution of an acid and react that with an unknown concentration of a base. Knowing that they will neutralize with each other, we are able to determine the point at which exactly the same amount of acid has been added as there is base present, called the equivalence point, where the number of moles of each is equal, and then using the volume that we have added and the concentration of that standard solution, we can determine the concentration of that initial substance. In a titration, it is very important to ensure that the concentration of the standard solution in the burette does not change, which is why before we start this experiment, we would always rinse the burette out with the standard solution to ensure that any liquid that remains in the burette is of that standard solution. When it comes to dealing with our unknown solution, what is most important to us is ensuring that the volume that is added is constant, and that is why we use a pipette, and which is why we can also use water to rinse out the conical flask, because it does not affect the volume of unknown substance that we have added. We know that the titration is a lab technique that is used to determine the concentration of an unknown substance. So the example we are going to be doing today is where we are titrating sodium hydroxide with hydrochloric acid. The hydrochloric acid here is our standard solution. We know that standard solution means that it is a known concentration. We also refer to it as our titrant. Then the sodium hydroxide that we'll be using is our unknown concentration substance. So we know it is sodium hydroxide, but we do not know the concentration. So the ultimate goal here is to add equal amounts of acids and base, and we can do that because we know that both of these are either a strong acid or a strong base, so they will completely neutralize each other with equal number of moles. So what we can do is, if we can determine an exact volume of sodium hydroxide, and then also, since we know the volume and concentration of hydrochloric acid, we would know how many moles of acid have been added, and with that we can determine the number of moles of base that were present, and from that the concentration.
So in order to find our initial, to get the known concentration or the known volume of sodium hydroxide, we use a pipette, and this pipette is marked as 25 milliliters, 25 or 0.0025 cubic decimeters. So that is 0.025 cubic decimeters. So we use this pipette filler to ensure that the pipette quantity exactly aligns with what it is marked as. We also ensure that it is the bottom of the meniscus that aligns with that mark. What we then do is we deposit this quantity of sodium hydroxide into a conical flask. We will see that the conical flask here does have some liquid present in it already, and that is because it has been rinsed with water, which is acceptable because the number of moles of sodium hydroxide does not change when we add it to water, so it is safe to rinse the conical flask out in water. It is important to remember, however, that the concentration within the pipette must remain constant, and so when we rinse the pipette out before using it, we do that with the substance to be used, in this case sodium hydroxide. We then, since this is a strong acid and a strong base, we can use bromothymol blue, which we know is blue in a base and yellow in an acid, but what interests us is the equivalence point here, which is the point where the quantity of acid has completely neutralized the quantity of base, and we know that that happens when this is a green color. So the titration is done with our burette here, where we use a stopcock valve or tap to deposit an exact quantity of the acid or the titrant present. Now we have done a rough titration already. A rough titration is one where you allow this to run a bit faster so that you get an idea of where you expect the equivalence point to be. In this case, we found in our rough titration equivalence point to be around 12.5 milliliters, and so what we can do is we can speed the reaction up until we get there, until we get close to around 12, at which point we would slow it down because we do not know at what exact point the equivalence would happen. Now, as you can see, the place where the acid is added to the solution already starts to a slight color change, which is why it's important to, as you move or as you titrate here with the acid, to continue moving this so that the acid and base mix entirely. What is also possible here and necessary is to ensure that there is no acid or base trapped on the side of this conical flask, so I would flush it out with water. Once again, this is allowed because the water is not changing the amount of acid or base that is present. It is only making sure that it is at the bottom of this conical flask. So what we would do now is you would allow the titration to proceed slowly by opening the valve very slightly. You would always hold the valve in your strong hand while allowing your other hand to slowly allow the mixture to happen. And as you get closer and closer to that expected equivalence point, I am now at 12.2, you would set the valve to drop the acid even slower. Once again, taking care to mix this properly because you do not want to pass the equivalence point, because then you do not know what exact quantity of acid is necessary to neutralize completely with the base. And what you can see here is it is literally one drop that takes the solution from being blue to being green. So we say that this is the equivalence point. We can read here that I've added 12.7 milliliters of acid, and now using this equation here, since the number of moles of acid must be equal to the number of moles of base, I know the concentration of the acid. I now know what volume of that acid has been added, and I know what volume of base was present to start with, so I can now solve for the unknown. What I'm now going to do is I'm going to add a bit more acid to allow this to proceed to what we call the end point, where you can see, there it's happened, you can see we reach an end point where there is now more acid present in the solution, and this is now turned yellow. So when doing a titration, it's very important to do it slowly enough so that you reach equivalence point and you can stop it there and take your measurement.